Hello, Mr. Boothman here, and we are getting ready to start on Unit 4. Unit 4 is all about sequences. We get into some mathematical proofs, and then we finish with some probability. So this is probably my favorite unit so far. I'm really excited to be able to explain all this to you, and why don't we jump right in? So Section 1 is sequences and summation notation. So we should probably start with talking about what a sequence is. We have it here in this box. I won't read the entire definition to you, but basically, a sequence is a function whose domain is the set of natural numbers. So the natural numbers we know, we write it as this. And the natural numbers are the positive whole numbers. Sometimes it includes 0, sometimes it doesn't. And then the values f1, f2, f3 are called the terms of the sequence. So really a sequence is an ordered list of numbers. And we usually write it with a subscript, a sub n, instead of function notation f of n for the value of the function at the number n. So here's an example of a sequence, 2, 4, 6, 8, 10. This is, of course, the sequence of even numbers. So using our sequence notation, we would write 2 as a sub 1, 4 as a sub 2, a sub 3, a sub 4, a sub 5, and so on. So with sequences, our goal is usually to figure out what the nth term of the sequence is. So for any natural number n, we want to know what that term is for the sequence. So to do that, we need to make a formula for the sequence. So here, if we're looking at our sequence so far, we think about it, a sub n, the nth term, is going to be 2 times whatever the term number is. Or a of n is 2n. Both notations are correct. So we can check this, make sure that it makes sense. A1 is going to be 2 times 1, which is 2, and we see that up here. A4 is 2 times 4, which is 8, and we see that up here too. So the nth term formula is really just us thinking about the sequence. There's not a whole lot to it, other than looking at it and trying to figure out what the term number has to do with the actual value of the number. So again, in general, 2n is our nth term formula for the even numbers. It's going to be important. This is something that comes up a lot, even numbers and then odd numbers, so we'll want to keep in mind what that formula is. So now that we have this formula, we can ask something crazy, like what is the 211th term in this sequence of even numbers? You could try to think about it, the even numbers, it's not that hard, but now we have a formula. Just plug in. So 2 times 2, 11. So the 211th term of the even number sequence is 422. That's all there is to that. Of course, there's more to it. More things we can do with this. So let's look at an example, a question you might see on a quiz or a test. Find the first 3 terms and then the 100th term of the sequences defined by the following. So we'll start with an easy one. A sub n equals 2n minus 1. So find the first 3 terms. That means a1 is 2 times 1 minus 1. 2 minus 1 is 1. a2 is 2 times 2 minus 1. 4 minus 1 is 3. A3 is 2 times 3 minus 1. That's 6 minus 1, which is 5. So I see that this is actually the odd numbers. So even numbers, a sub n equals 2n. That was the evens. The odd numbers, a sub n equals 2n minus 1. Things to keep in mind. So then we also wanted to know the 100th term of the sequence. So a100 is 2 times 100 minus 1. 200 minus 1 is 199. Great. I'm going to have you try B on your own, but I'll work through letter C with you. R1, And notice we can change that A to T or to R to any letter we want. It doesn't change what we're doing, just a different way of differentiating between the sequences. So R1 is -1 to the first power over 2 to the first power. So that's -1 over 2. R2, -1 squared over 2 squared. -1 squared is +1 over 4. R3 is -1 cubed over 2 cubed. -1 cubed is -1 again over 8. And then R100 is -1 to the 100th power over 2 to the 100th power. -1 to the 100th power, 100 is even, so that means -1 is going to be turned into +1 over 2 to the 100th power. You can plug that into a calculator if you really want to know what that is. So we see that -1 to the nth power, that part of this nth term formula, is making our sign alternate. We have a negative and then a positive. Negative, positive. So anytime we want a sequence to alternate signs, it's -1 to the nth power, starting with a negative. Something else to keep in mind, especially for this next example. So now we want to find what this nth term formula is. So a lot of you aren't going to like me because I'm going to say that a lot of this unit is about thinking. There's no clear-cut, this is how we do this. Especially for these sequences, it's a lot of thinking about what we want, what we need to accomplish here, and trying to find a way to make that happen. So I'm looking at this sequence, and I see that the top numbers are the odds, and the bottom numbers are the evens. So we said above, we have formulas for the even numbers and the odd numbers. So A sub n is equal to, I want my odd numbers over my even numbers, 2n minus 1 over 2n. And I can check this for a couple of different term numbers. If I plug in 1, I'll get 2 minus 1, which is 1 over 2, 1/2. That is the first term, so it looks like I'm good. And that's all there is to A. In general, finding the nth term formula isn't that work-intensive. It is just thinking about what we want and what we need. For letter B, I see that we are alternating signs. So we said before, from letter C in the first example, that alternating signs, starting with a negative, means that I need -1 to the nth power. That's going to make my sign alternate. And then I'm doubling, 2, 4, 8, 16, 32. So doubling is 2 to the nth power. So again, this is alternating signs. And this is doubling. And I can check that for some term numbers, and I see that this is the correct nth term formula. It's important to note here that not all sequences can be defined by a formula. So for example, there's no known formula for the sequence of prime numbers. The prime numbers are incredibly interesting. In fact, there's a whole field of mathematics called number theory that deals heavily with integers and with the prime numbers. We can talk about that separately if you'd like. I'm always here to discuss cool math stuff. Now, sometimes the nth term of a sequence may depend on some or all of the terms preceding it. So, if we don't have a formula like this is what we would call an explicit formula, where all I need is the term number and it gives me the value of the term. Sometimes we're going to have something like an example 3 here, where the nth term formula is defined based on the terms before it. So I might not know what the, I won't know what the term value is going to be unless I know the term value before it. So this kind of sequence is called recursive. Recursive sequences are very important, and they turn up a lot in math. So find the first 5 terms of the recursively defined sequence if a sub 1 equals 1. So that's important. We need that information so we can get started. If a sub 1 equals 1, well, they gave me the first term then, so I only need to find 4 more. a sub 2 is 3 times a sub 2 minus 1 plus 2, which is 3 times a sub 1 plus 2, which is 3 times a sub 1 is 1 plus 2. 3 times 3 is 9. So I'll do one more for you, and then I'll have you find the fourth and fifth terms. A sub 3 is 3 times a sub n minus 1. So the term before a sub 3 is a sub 2 plus 2. A sub 2 we just found was 9, so this is 3 times 9 plus 2. 9 plus 2 is 11, so 11 times 3, 33. And again, you can find a sub 4 and a sub 5 on your own. Example 4, this is so cool. I love talking about this, and I'm sure it'll be familiar to most of you once we give it a name, but let's look at the definition. Find the first 11 terms of the following recursively defined sequence if f1 equals 1 and f2 equals 1. So the nth term of this sequence is defined as fn minus 1 plus fn minus 2. What does that mean? Let's think about it. That means that each term is equal to the sum of the previous two terms. So I'm starting with 1 and 1. That was given to me here. And then the third term is going to be the first term plus the second term. 1 plus 1 is 2. The fourth term is the second term plus the third term. So 1 plus 2 is 3. The fifth term is the third term plus the fourth term. 2 plus 3 is 5, and so on. I want 11 terms this way, so 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 21 is 34. 21 plus 34 is 55. That's 10 terms. I need one more. The 34 plus 55 is 89. This is a really interesting sequence. It's one that we find everywhere in nature. We're not quite sure why, but it is something that naturally occurs all the time. And this was discovered and so is named the Fibonacci sequence. So I'm sure most of us have heard of this. We can talk about some really cool examples of this in class where this shows up in nature. There's all kinds of cool examples, so I'm looking forward to talking about that. But moving on for now, that's really all that we have to say about sequences in general. Now, there's cool stuff that we can do with sequences, and that's the second part of the section here, the partial sums of a sequence. So if we have a sequence like this, we have a special word, the partial sums, and we write that as S all the way to S sub n, where we're just adding terms up to the partial sum that we want. So S1 is called the first partial sum, S2 is called the second partial sum, and so on. So Sn is called the nth partial sum. And then if we write these partial sums in a sequence, we call that the sequence of partial sums. So find the first three partial sums and then the nth partial sum of the sequences given by, so letter A, here's the sequence we're given, so S1, that's just A1, which is defined as 1 over 2 to the first power, or 1/2. S2 is A1 plus A2, and I'm just looking up here. A1 is 1/2, and then A2 is 1 over 2 squared, which is 1/4. A half plus a fourth, that's 3/4. S3, that's A1 plus A2 plus A3. So A1 plus A2 we found was 3 over 4. So this is 3/4 plus 1 over 2 cubed. 3/4 plus 1 over 8. and that's 7 over 8. And then the nth partial sum, that's just Sn equals, well, that's 1/2 plus 1/4 plus 1/8, and so on. Whenever we see those three dots in math, and we use that a lot, especially in this whole unit, that just means it continues just as it was. So 1/2, 1/4, 1/8, 1/16. I'm just following this formula. All the way to 1 over 2 to the nth power. And I can't really add that up because I don't know what n equals, so that just is my nth partial sum of the sequence. Go ahead and try letter B on your own, and we can talk about that in class. So that's an interesting example as well. Now, I'm sure you're sitting there thinking, well, that's a lot to write out. I don't really like having to write out partial sums like that. And I would completely agree, that's annoying, especially since we use partial sums a lot in math. That would take us way too long if we had to do that every time. So, mathematicians thankfully have come up with some special notation to shorten this long expression, and we call this summation notation or sigma notation. Sigma notation, sigma is this Greek letter, so perhaps we've seen this before. So given a sequence, we can write the sum of the first n terms using this special notation, summation or sigma notation. So this whole sequence right here, and if we compare that to this up here, we see that this is really just Sn. We can write that as this fancy expression. We have k equals 1 on the bottom, n on the top, and then a sub k. So here's a helpful graphic to tell us what this means. So the sigma is just telling us that this is summation notation, that we are adding sums here. So it doesn't really, like, we're not doing anything with it other than it telling us what we're doing. The number on the bottom here tells us what we're starting with for this expression. And then the number up top here tells us what we're ending with. So let's go ahead and take a look here through some examples, because that would be way more useful than me just talking about that notation some more. I'm not sure why this erased here, but these should be summations. So find each sum. Here we have k squared, and our sigma tells us we're adding. And k equals 1 on the bottom, and then 5 on the top. So that means I'm starting with k equals 1 and ending with k equals 5. K squared, if I start with 1, that's 1 squared, plus 2 squared, plus 3 squared, plus 4 squared, and then I'm ending with 5 squared. So I'm just plugging the numbers 1 to 5 into this expression. And that's what I end up with. 1 plus 4 plus 9 plus 16 plus 25. If I add all of those together, it's 55. And that's all that this means. I know it looks really foreign and odd to us, but this is what sigma notation is telling us to do. So it's actually pretty simple. So for letter B, I'm starting with j equals 3 and ending with j equals 5, and my expression is 1 over j. So starting with j equals 3, and I'm adding, because of the sigma, 4, and then I'm ending with 5. And so if I get a common denominator and add these together, that's 47 over 60. Go ahead and try C on your own. So this is just I, that's all I'm doing inside, and then I'm starting with I equals 5 and ending with I equals 10. We'll talk about that in class. Now, our final example for this section, I know it's been a little long, but sequences, they're kind of new and interesting to us, so I wanted to make sure that we get a good introduction to them. Write each sum using sigma notation. So now we can work backwards. Instead of being given the sigma notation, we're given a sum, a partial sum, and we want to work backwards and get our sigma notation from this. So how do we shorten this whole partial sum? Well, what is each number doing? I'm cubing each number, so that's going to be k cubed. That's what my term actually is. I am summing, so I want sigma. And then I'm starting with k equals 1, and I'm ending with 7. And that's it. That's my answer. So you should be able to work from one to the other in either direction. For letter B, what am I doing to each number? I'm taking the square root, so this should be the square root of k. I'm adding, summing. I'm starting with k equals 3, and I'm ending with k equals 77. And that's all there is to it. All right, so we're going to practice this some more in class. Until then, make sure that you are watching parts of this video that didn't make sense to you, that you're watching this video in general. I thank you for watching to the end. And we'll jump into some special kinds of sequences in the next couple of sections. Until then, thank you so much.